In this lecture, we are going to look at some of the commonly occurring continuous random variables in structural reliability problems. I have this list, which is also in your course material, of such continuous random variables. Of these, we will pick up the uniform, the exponential, and the gamma for further discussion. And in the normal family, we are going to look at the normal and the log normal distribution today. And finally, in the extreme value family, we are going to discuss how the Gumbel, the Frechet, and the Weibull distributions arise. So let's start with the uniform as we did in the discrete case. Like in the discrete case, no outcome in the range is more likely than the others. So the density function is a rectangle between A and B, and the distribution function, the CDF, is a straight line between A and B going up from 0 to 1. And the mean is the average of A and B, and the variance is the difference square divided by 12. If A is 0 and B is 1, we have what is known as the standard uniform distribution, which is very important in generation of random numbers, which we'll see next week. And as I said, the application is in random number generation, and whenever we have no reason to prefer any outcome over another in a given range of values, the uniform is the natural choice. Let's discuss next the Poisson process. So let's look at the timeline as you can see on the screen, and let's start with defining a point process. So a point process is basically occurring of random points, and it can be described in any one of 4 equivalent ways. The counting process, the number of points up to the time t, the increments of the counts over an interval, the arrival times of the points, the occurrence times, or equivalently, as I said, the inter-arrival times. So those are the taus. The arrival times are the t's, and the inter-arrival times are the taus. Now, a point process is a renewal process if the taus are IID random variables. Further, it's ordinary if there is no clustering of points, and it's pure if the first occurrence time or the first inter-arrival time is no different than the others. And now, a pure homogeneous Poisson process is a special kind of renewal process which has the probability of one occurrence in a small interval delta t equal to a constant times the length of that interval. So it's proportional to the interval length, and there may not be 2 or more occurrences. There can be either 0 or 1 occurrence only in a small interval of size delta t. That gives us a pure homogeneous Poisson process, and we get some very powerful results out of it, that the inter-arrival time, the taus, are IID exponential random variables with that same parameter lambda. So its mean is 1 by lambda. The counts in a given interval of size t is a Poisson random variable, which we have already seen in the discrete case, and that has a mean of lambda times t. So lambda is the rate and t is the length of the interval. And sometimes it's also very useful to use the fact that if we know the number of occurrences in the interval 0 to t, then the occurrence times, the t's, are uniformly distributed in that interval. So we have 3 very important random variables occurring from a Poisson process, The exponential, which is basically the time to the first occurrence, its discrete counterpart is the geometric. The Poisson, which we have already seen, it's the number of occurrences in a fixed time interval, so its discrete counterpart would be binomial. And the Erlang, which is the time to occurrence number k, and its discrete counterpart would be the negative binomial or the Pascal distribution.